Hey guys, I hope you're well. Sorry I'm not there today. It's been hit a little bit with a cold/flu. I don't want to infect others, so hopefully I'll be back tomorrow though, and we'll be able to do a few things in person. Look, today we're doing the trapezoidal rule. Now I know I would like to have been doing this in person because there will be some questions, but I still wanted to make a video regardless, so you have the opportunity to pause it, to replay it, because I think as this seems to be the area of integration, no pun intended, of course, that is being examined. Okay, now that was last year on the May paper, the November paper. It may not be this year, but certainly it's worthwhile for us going through in detail on this. It's under our integration chapter in OneNote, Tuesday, week 9A. There's the exam question we'll go through as well. But let's get cracking. Now, on the front of this, or top of this, I've put in the trapezoidal rule formula. Okay, now that's on the formula booklet, so no need to remember that. We just need to know how to use it. I will also show you an easier version of the formula that might be a bit easier to use. But look, we know that the trapezoidal rule is basically used to find the area beneath a curve. Now, it is an estimate. So when I spoke about this last week, I know that we know how to find the exact area. If I asked you to find the exact area beneath the curve, what I'm hoping you would do, you would find the integral of x squared dx between the values of 0 and 4. Okay, this was if we were doing the exact. Remember, this was called Riemann's integral. So if we did the antiderivative, it would be x cubed on 3. If I use my correct notation, okay, we use those square brackets 4 and 0. We would then sub the 4 in, we'd sub the 0 in, and then we would find the difference of those two values. So 4 cubed on 3, subtract 0 cubed on 3, and that would simplify out to being, I think, 64 on 3 units squared, or whatever the mixed numeral that might be. Now, again, that is if you were to find the exact, and right underneath there, the exact area. So before they worked that out, right, before they figured out the relationship between the integral and the area, what they were doing, they were estimating. Now, I think in class we spoke about different methods. We could, find rectangles like that. For example, we could do 2 rectangles nice and quickly and find the area that way. But of course, you can see that's not a very good estimation. We might decide to use, if I get rid of those, we might decide to use smaller rectangles, for example. So instead of using a width of 2, we might make them into smaller ones like this. Okay, albeit still not particularly accurate, but more accurate. We could keep on reducing the size of those rectangles. But one of the things we said we could also do was maybe use trapeziums, right? If I use 2 trapeziums, that's more of a triangle, I guess, but the second trapezium would look like this. That's pretty accurate, right? I mean, it's not perfect, but certainly, we're going to see we have a little bit extra area, so it might be a little bit over 64 over 3. But of course, we could then find smaller trapeziums, for example. Just like we did with the rectangles, we could use a width of 1, like that, for example. And that would be, I guess, even more accurate than what we had previously. Now, we could go even further and make 8 trapeziums, whatever it might be. And the smaller we do it, the more accurate it's going to be. Now, when we're doing this, again, I know why bother, because we can find the exact, why even estimate. But like anything with life, history is important to us, right? It's important to know where we came from. So although this is really an outdated kind of process, it is something for us to be mindful of. We will be examined on it, and it's important to know where we came from. So what I'm going to do, I'm going to start by ignoring the formula above that and show actually how we get to that formula. Now, I'm going to use 4 trapeziums here between 0 and 4. I could use just 2 and use 0 to 2 and 2 to 4, but I'm going to use 4. So basically, we're going to use 4 applications of the trapezium rule. Now, can you remember what the rule is to find the area of a trapezium? I'm hoping you remember this to be something like A equals a half times the height times A plus B. You might use A equals H on 2, A plus B. You might even say A equals A plus B all over 2 times height. There's lots of different variations of that particular formula. Now, for today's process, I'm going to use that middle one for the area of one trapezium. And basically, I'm going to apply that 4 times. Now, I know that the very first one looks more like a triangle, but we can still use it as a trapezium. Okay. Now, what is the A plus B again? If you cannot remember these formulas, all right, I'm going to draw my trapezium like this. So it's in the same kind of format as our trapeziums. The A and the B are always the parallel sides. And I guess in our case, the height, is that perpendicular height there. So each time, I guess the A and the B are the Y values of our graph. And the height is the difference between each of those X values. So I guess, our height would be that distance there. And what you'll see when we're doing this question, gents, you'll find that the height will always be consistent. The height will always be the same. We're not going to use irregular different types or sizes of trapeziums. We're going to use consistent heights for all of them. Okay. So if I apply this formula right to the very first one, let's call it area 1, and I'm going to kind of do this little one. I know it looks like a triangle, but I'm going to do it in green. We would say height divided by 2. Now the height is between 0 and 1, which means it's 1 over 2, right? And then the A plus B, well, how high is that particular trapezium in green? Well, it starts at 0, so we know it's going to be 0. And then how do I get the height? I'll put it in green arrow there. Well, the rule, we can see it's 1 because we've already got the graph there, but the rule says y equals x squared. Well, x equals 1, so 1 squared is simply 1. And that's the area of my first trapezium. Now, if I want to find the area of the second trapezium, I'll do this one now in sort of a blue color, as such. I'm going to add on. Now, the height is still between 1 and 2. It's still 1, so 1 over 2. Remember, the height is the h over 2 times a plus b. Well, the height of that is that green line still. Well, that's what we just did that last one, right? That's 1 squared is 1 plus, and now the formula says 2 squared, but you could put 4 if you wanted to. So that value there is 4, of course. All right. And then I need to do the next one. Now, I'm going to move that down a little bit because we're going to do 4 applications of this. Yeah, I know, it's pretty lengthy, right? It is pretty lengthy, unfortunately. Let's do this one in yellow. So this particular trapezium here in yellow, I'll do yellow writing 2. We've got height on 2, so that's 1 on 2. Now, we've still got the 4 again because that's the left-hand side, plus, and now it's 3 squared. Okay. I'm going to leave that as 2 squared, by the way, just because I've got it there. And that's, again, because the formula says y equals x squared, 3 squared is 9, so the height is 9. I've got one final trapezium at the back end. Let's do this one in like a pinky color. You won't have to do more than really 4 applications. 4 applications is probably the biggest amount. So again, 1 over 2 is my height. My height is between 3 and 4. And then my left-hand side, of course, is 3 squared, which is 9. And then the last one is 4 squared, and 4 squared is 16. Now, again, those values are coming from knowing that the formula of the graph is y equals x squared, right? It's the y value. It's how high those amounts are. That's 16. And then literally I'm adding that all together, right? That's all I'm doing. I can do it on my calculator. Now, of course, we might be able to condense that to look a little bit nicer. So, for example, what's in or common in all 4 of those areas of the trapeziums? Well, they're all being times by a half, right? So I can, in fact, factorize that half out and then write it as 0 plus 1 squared, because that's really 1 squared, which is 1, plus 1 squared plus 2 squared plus 2 squared plus 3 squared plus 3 squared plus 4 squared. So all I've really done there is I've factorized that half out, and what I'm left with is all these things here in those brackets. Now, what else do you notice is interesting within that piece of working? Well, hopefully what you might recognize is I've got 2 lots of the 1 squareds. I've got 2 lots of the 2 squareds. I've got 2 lots of the 3 squareds, but I've only got 1 of the first value and 1 of the last value. So again, if I wanted to, condense this even further, I could say something like 0 plus 4 squared, that's the first plus the last, plus 2 lots of 1 squared, plus 2 lots of 2 squared, plus 2 lots of 3 squared. I know. Now, I know you wouldn't bother factorizing this in a question you just literally put into your calculator, but there is a purpose to my madness, as there often is. I'm going to factorize again because what we've also got is a 2 now in the middle of those things. And I'm just factorizing things out to make it look a little bit nicer. Now, that technically speaking there is a little bit faster than that first line of working, but it all means exactly the same thing. The reason why I factorized all of that out, and now I'm just going to get this thing here and copy it and bring it down so I can make it nice and big, is that what I've actually done here is almost exactly what is in this formula. And I want you to see the differences. Because if you think, right, we can see where the first value and the last value, they're different, but you've got 2 of these each time. Each time you've got 2 of those height values or y values. And so what we end up coming is factorizing, there's that half. Okay, half times the height. Now, our height was 1. So just making sure you understand that. Our height was 1 in this case. Y0 plus yn, well, that's the y value of the first and y value of the last part. Again, 0 and 4 squared is 16. And then we've got 2 times all those middle functions, 1 squared, 2 squared, 3 squared, because when I had my trapeziums, it looked something like this, didn't it? If I split them right out. Okay, so you can see I've got 2 of those middle terms every single time. Okay, 2 of those middle terms. So you can again see from the formula, and I'll do it in yellow on that little pink bit that I've just got there. In fact, I'm going to zoom right in. I got the first and the last height in yellow, sorry, and then in green, I've got 2 lots of the middles. 2 of those, 2 of those, and 2 of those. And that's where my little rule comes from, right? It says basically, and this is where I like to kind of write this rule a little bit differently. I say it's h on 2 function of the first plus function of the last plus 2 times the functions of the middle terms. Okay, where the function is whatever, in this case, we'll y equals x squared. So it's 1 squared and the last term squared, and then 2 times all the middle ones. This height, b minus a on n, that can get confusing. All the height is the consistent height between those values. Is what it's going up by. And then my x values, of course, in this particular graph. Now, why it says b minus a over n, well, b and a, if you think about our integral, are 0 and 4, and n is the number of subintervals. Now, a subinterval are how many trapeziums I've got. So if you think about this rule, and again, I don't really like the b minus a over n, but in this case, b was 4, so a was 0, and n, we have 4 different trapeziums. And what's 4 divided by 4? 1. And that's how we got our height. Our height was 1. Most of the time, gents, you can literally just look at it and see it. Now, I know that sounds confusing sometimes, but we're going to look at some questions, and actually it's pretty straightforward when you start applying it to questions. Now, of course, we haven't found the value of that yet. So let's actually find the value and see how close we were to the original amount. So I'm just going to go into menu 1. I'm going to do my 0.5. I'm going to open my brackets. we have 0 plus 16. I mean, you can do 4 squared if you want, plus 2 times 1 squared plus 4 plus 9. Again, you can do the squares if you want. All right, chuck it all equals. We get 22. So our approximation here is 22 units squared. Now, if we go back to have a look at our actual exact value, 64 divided by 3 equals 21.3 recurring. So that's the exact value. Look, that's pretty close, right? We're off by 2/3. That's pretty close. So you can see if I've applied it 4 times to 4 rectangles, it's actually pretty accurate. And the more rectangles I use, or more trapeziums I use, sorry, the more accurate it's going to be. All right, let's look at a question and how it works. As I said, gents, I will be in tomorrow, so if this is confusing for you, don't stress out too much. All right, this is a Hsc question. A field is bordered on one side by a straight road and on the other side by a river, as shown. Measurements are taken perpendicular to the road every 7.5 meters along. Now that's important, right? That's 7.5, that's 7.5, that's 7.5, that's 7.5. What it's kind of alluding to is that the height or the width between each of those trapeziums is 7.5 meters. Now, they might give you an actual function that you have to go and find that with, but often they just draw little diagrams out, right? Which makes it much easier. And it says use 4 applications of the trapezoidal rule. Well, that means 1, 2, 3, 4. This means 4 sub-intervals. And that's pretty straightforward. So my rule says area equals approximately h on 2 function of the first plus function of the last plus 2 times the functions of all the middles. Now I know we can use the formal one, but it means the same thing. So what this means is my height is simply 7.5 meters because it's the width between each of those little trapeziums. Okay, so if this is a trapezium, for example, that's what we're estimating. That's one trapezium. This is another trapezium. This is another trapezium. And this is another trapezium. Okay, it's not going to be perfect, but we're going to estimate it. So 7.5 over 2. Now, function of the first. Now, there's no need, because I don't need the actual equation of this function. They are actually telling me what the heights are or what the y values are. This is 8.8 and this is 7.1. This is 9.8. This is 8.5. This is 4.9. So the first function or value is simply 8.8 and the last function value is 4.9. And then I'm going to do 2 lots of all the middle ones. And can you see again why I'm doing 2 lots of them? Because 7.1 is in the first trapezium, but 7.1 is also in that second trapezium. So that's why we're doing 2 times those amounts. So 8.8, oops, not 8.8, that's the very first one, wasn't it? Naughty, naughty. 7.1 plus 9.8 plus 8.5. And that's it. That's all I'm doing. That's literally what my rule says to do. Okay, it's actually not that hard when you think about it. The issue is they can present the questions sometimes in different formats. Okay, but now I'm going to put 7.5. I'm going to open my brackets. Oops, I'm going to make sure it's over 2. Okay, because it's h on 2. Perfect. Open brackets. We're now going to do my first, which is 8.8 meters. I'm going to do my last, which is 4.9 meters. And I'm going to do 2 times all the middle term because they're all my double ups of my trapeziums. 7.1 plus 9.8 plus 8.5. Hopefully you're kind of getting the gist of this. Now, we get approximately 241.875. And of course, we could say to 3 sig figs, 242. And I'm going to go back to the question. It's meters and it's squared. And that's it. Job done. That's our first question, really, for the trapezoidal rule. Okay. Now, of course, with that, we'd be looking probably for an M1 for an application to the Simpson's rule. I'd probably give you an A1 for a correct substitution and A1 for the correct answer. Job done. Now, they're nicer questions when they give you the kind of drawn out like that, because you can see clearly what these values are here. They could also put this in a table. You know, they could do something like this. So this is my X values, my Y values. X would be like starting at, well, actually, in this case, it's starting at 7.5, for example. I might say I start at 0, for example, and there might be 7.5, there might be 15, there might be 22.5, and that was 8.8, that was 7.1, that was 9.8, that was 8.5, etc. They could put it in table forms like this, okay, or they could give you simply the equation. All right, and again, you can clearly see here, that's the first value, the 4.9 will be the last value, and then you got 2 times the middle values. It's not much more different, but I see in IB they tend to do that a fair bit, and so this is an example of doing that. Inspectors are investigating the carbon dioxide emissions of a power plant. This was last year's November question, by the way. What have we got? It says, let R be the rate in tonnes per hour which the carbon dioxide is being emitted, and T be the time in hours since the inspection began. When R is plotted, blah, 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 blah. I don't care about that. What I care about is this table. Okay, my X values, my Y values, and my function values. And it says, use the trapezoidal rule with an interval width of 0.4. Well, the minute I say interval width of 0.4, that's telling me that the height is 0.4. That's the width of my trapeziums. Okay, now for this question, if you wanted to draw this out, you could kind of draw your trapeziums out if you wanted to, and I don't know, you could do it like this and have, you know, that's 0 and it goes up to 30, for example, and then 0.4, and this is going to go up to 50, and then this is 0.8, it's going to go up to 60, and you can start to see how my trapeziums are going to start to shape out. 1.2 goes up to goes down to 40, so like, I don't know, like here somewhere, it's another trapezium. Okay, what else we got? We got well, that's 1.2. 1.6 goes to 20, a bit further down, and then 2 goes in between, back up to 50. Okay, that's what it kind of looks like if it was drawn out. But I just need to use my rule. Okay, area equals h over 2, function of the first plus function of the last plus 2 times the functions of all the middles. That's it. Okay, so the height, we're being told that the height of each of these trapeziums is 0.4. It said it in the question, right? So it's nice and easy. Approximately equals to 0.4 over 2. And then the very first height I'm looking at was 30, and the very last height was 50. Perfect. So I'm going to put 30 plus 50 plus 2 times, and now I'm doing all the middle terms. 50 plus 60 plus 40 plus 20, and then it is simply a matter of me throwing that into my GDC. So not that hard, is it, really? 0.4 all over 2 brackets. I've got to have my, of course, if you want to do things like 30 plus 50 is 80, that's fine. Okay, take shortcuts if you know what the answer is going to be. 50 plus 60, working out is very important, as it always is, gents. Okay, so make sure you do have your working out. And then make sure I close my brackets, press equals. So we have the area is approximately equal to 84. Now, I just want to double check what the measurements are in. What is it in? Tons. Perfect. Job done. My first part of my question is done. That's last year's IB question that students really, really battled with. They couldn't do that question. And when you look at it, it's not that hard. They just had not studied it. They had not revised it. So very, very important to make sure you guys revise this. The last part of this is a revision right the way back to beginning of year 11 with percentage error. Okay, now I think percentage error, if we go back to our formula sheet, again, I like reflecting around our formula sheet because you should be looking at it all the time. Okay, there's trap rule under calculus. But if we go back all the way to topic 1, I believe it's in. All thereabouts, there it is. Percentage error. I'm just going to snapshot that little guy out and then go back to my questions. How do people get this wrong? I don't know. Okay. So now we're going to go through this one, and it says percentage error equals value of the approximate. Well, our approximate was 84. Subtract the value of the exact, and we're told exact is 72, and that's the absolute value of all this, by the way, all over 72 times by 100. And that makes sense again because you're saying, well, what was the difference between them, and divide it. It's a percentage of that amount, that exact amount. So again, all I'm going to do on my GDC is put 84, take away 72, which of course is going to be a negative value, divide that by 72. I want to make it positive. Okay, oh, it's a positive value, so my bad. Times it by 100, press equals, and we get 16 2/3%. Or 16.16 recurring percent, or 16.7%, or thereabouts. And we've just found our percentage error. And congratulations, you've just knocked yourself with 5 out of 5 marks. It's not a hard question, gents. Okay. I know I've said that trapezoidal rules is difficult. It's not that difficult, realistically, as long as you know how to use that rule. If I come back to the question here, gents, there's my rule. You can see again, it's half times the height, first plus the last, plus 2 times all those middle functions. Okay, the height is given by the so the last number by the first number divided by the number of sub-intervals. But most of the time, I'm going to tell you to draw the question out. Now, that's pretty much me done. But if you would like to look at a harder question and you want to listen on, do so. This came out from the Standard 2 paper last year, the year before, I think it was, in HSC. So it's a HSC question, but I really, really like it as a hard question. So again, if you want to go do the questions, go on and do the questions. I will just double check before I do this. 13A2. I might just, sorry, gents, I might just take a tack and just do this question here, because you might struggle here. 4 sub-intervals. Okay, I'm going to do it on here. So I was about to go through that other question, but let me just do this one first. Just so you can see a different style of question. This one, it's asking you to use 4 sub-intervals. It said that. Now, a lot of the time, what I'm suggesting is, what you can do is put, 1, 2, 3, 4. You don't have to draw it out properly, but you can draw out 2 over root x and see what it looks like. But let's just say, for example, between 2 and 4, let's say, for example, you got this graph here. Just making the graph up, to be honest. But that's between 2 and 4. That's one application. We want 4, which means that's 2 currently. So if I split that again, now we've got 4. So hopefully you can see that splits. You can see how I've got 4 intervals. So when it wants 4, you just have to kind of figure out very quickly how you split into 4. Again, if you're looking for the common height, we say b minus a over n. B is 4, a is 2, and we want 4 sub-intervals. 2 over 4, and that equals 0.5. And now you can clearly see here that this is going up by halves, right? 2, 2.5, 3, 3.5, 4. Nice and easy. Now, the only other hard thing about this question, is why I wanted to do it, is when you use the rule, h on 2 function of the first plus function of the last plus 2 times the functions of all the middles, they don't give you the y values. Okay, there's my h on 2. Now, we aren't given any of these values here. And that's what makes this question a bit more challenging. But what we do know is that the function is given by 2 divided by root x. Well, let's substitute that in. We have the first value would be 2 over root 2. That's the first value. The last value would be 2 over root 4. Then we've got 2 times all the middle functions. Well, that's going to be 2 over root 2.5 plus 2 over square root of 3 plus 2 over the square root of 3.5. Now, how do I get all those values? Well, I just subbed in my x values into the actual function. That's all those things are. Now, this is where it's a slightly harder question because it gave us the rule to find the y values. It didn't start with the y values. Now, it could have given you a table of values, and if it gave you a table of values for this question, it would look like this. Technically speaking, my x values, my y values, 2, 2.5, 3, 3.5, and 4. And you can see now by using 5 values, 1, 2, 3, 4, 5, it creates those 4 subintervals. And then all I'm doing to get my y value, of course, is subbing in the x value. And this is what it would look in table form. And so that last question literally was saying the first plus the last plus 2 times all the middles. This is exactly the same question. It's just they gave us the actual rule to find those. And because they said there was 4 subintervals, we had to work out how many or what that height value was going to be. It's basically kind of like the average, I guess. 4 minus 2 divided by the number of subintervals. I like sketching something out. Doesn't even matter if the graph is not correct. That doesn't really matter as long as you got the function on there. It's mattering of figuring out how many pieces you have and then that making what's the height going to be. Okay, in this case, the height was a half because we're going from 2 to 2.5 to 3 to 3.5, etc., etc. Okay, now this has been going on for a long time. I'm just going to double check my timing on this, gents, because it's a long video. What are we on? 33 minutes, gents. If you are still with me, that's a miracle. As I said, pause it and go on to some questions. But if you want to have a look at this last question, it's quite a nice one. Okay, find an expression for the area of the cross section using the trapezoidal rule. Well, we know the rule says the area equals approximately h on 2, function of the first plus function of the last plus 2 times the functions of all the middles. That's the rule, right? Now, in this case, we don't know what the height is, so the height is h. We know the first function of value is 0. The last is also 0. The middles are a plus b plus a. Perfect. And now if I simplify that, we get h on 2. We get, 0 plus 0 is 0. We get 2 times 2a plus b. That makes h on 2 4a plus 2b. And that is my expression. Wonderful job done. Thereabouts. Okay, and then the last part says the area of the cross section must be 600 meters squared. The tunnel is 80 meters wide. Well, if the tunnel is 80 meters wide, what does that mean about our height? Well, the height must be 20 each time. So that's nice. I can put the 20 in there for the height. The area we're being told is 600. Perfect. And now I've got this 4a plus 2b. Whatever a and b are, we don't know. It doesn't really matter so much. Now, if I get an expression for 4a or 2b, whatever it might be, that's going to be 600 equals 20 divided by 2 is 10, 4a plus 2b, which is make it 60 equals 4a plus 2b. Let's just halve everything to make it easier. 30 equals 2a plus b. Now, again, this is a much more challenging sort of question because it says the value of A increases by 2 meters. By how much will B change? Well, it's veggie maths, right? There's no real numbers for A and B. Now, of course, I could let A be a number and then increase it by 2 to see what happens. So, for example, let's get an expression for B. 30 minus 2a, because that makes it a little bit easier. Let's say, for example, if we want to do it non-algebraically, when a is 5, right? B equals 30 minus 10. B would equal 20. Now let's decrease a, or are we increasing it? We're increasing it by 2, makes 7. So we get B equals 30 minus 14. B equals what's that going to be? 16, which means B has decreased by 4. There you go. Now that kind of makes sense because if I want to do it algebraically and I increase A by 2, what you get is 30 minus 2a minus 4. The only difference is this subtract 4. That's it. So something about decreasing it by 4 would be perfect. Now, gents, this has been a terribly long lesson, and I apologise. My daughter has now rocked in, so that tells me that we're done. Hello, my darling. I hope that made sense, and fingers crossed, gents, that yeah, you can start working on some of these questions, particularly on 13A.2. Start working your way through, and if it doesn't make sense, all good. As long as you've got some notes in your book, we'll go through this in class tomorrow. Have a wonderful day, guys, and I'll see you tomorrow. Fingers crossed.